Hi friends, today we discuss about the formula for energy stored in a capacitor. Let's discuss about the derivation of the energy stored in a capacitor step by step. The energy stored in a capacitor is nothing but the electric potential energy and is related to the voltage and charge on the capacitor. This energy is stored within the electric field created between the capacitor's plates when a voltage is applied. A capacitor stores energy as electric potential energy, which is the energy stored in the electric field created by the charged plates. If the capacitance of a conductor is C, then it is initially uncharged and it acquires a potential difference V when connected to a battery. It means when an uncharged capacitor is connected across the battery, then potential difference between the plates of capacitor increases from 0 to the value of electromotive force of battery. But battery supplies charge at the constant potential difference. If Q is the charge on the plate at that time, Q that equals to CV. This is the equation number 1, where the equation Q equals to CV represents the fundamental relationship between the charge Q on a capacitor, its capacitance C, and the potential difference V across it. This equation states that the charge stored in a capacitor is directly proportional to the voltage applied across it, where Q represents the charge stored on the plates of the capacitor, charge measured in coulombs. C represents the capacitance of the capacitor, which is a measure of its ability to store charge. It depends on the physical characteristics of the capacitor, such as the area of the plates, the distance between them, and the type of dielectric material between them. Capacitance measured in farads. V represents the potential difference or voltage applied across the capacitor's plates. This is the electrical pressure that drives the flow of charge. Voltage measured in volts. In simpler terms, imagine the capacitor like a container that can hold a certain amount of charge. The capacitance C determines how much charge the container can hold, and the voltage V determines how full it gets. The more voltage you apply, the more charge you store. According to the formula, Q equals to CV. Rearranged the above formula, that is V equals to Q by C. This is the equation number 2. The formula V equals to Q by C represents the relationship between voltage V, charge Q, and capacitance C in a capacitor. Specifically, it defines voltage as the ratio of the charge stored to the capacitance, where V represents voltage across the capacitor measured in volts. Q represents charge stored on the capacitor measured in coulombs. T represents capacitance of the capacitor measured in farads. The formula essentially states that the voltage across a capacitor is directly proportional to the amount of charge stored and inversely proportional to the capacitance. A higher capacitance means the capacitor can store more charge at a given voltage. The work done is equal to the product of the potential and charge. That is, W equals to VQ. In simpler terms, the equation W equals to VQ signifies that the work done to move a charge through a potential difference is equal to the product of the potential difference and the charge. This formula is fundamental to understanding electrical work and energy in circuits, where work done W represents the energy required to move a charge against an electric field. Potential difference V represents the indicates the difference in electric potential between 2 points in space, which is the driving force behind the movement of charge. Charge Q represents the amount of electric charge being moved. This equation is used to calculate the work done by a battery in pushing a charge through a circuit, or the work required to move a charge in an electric field. If the battery delivers a small amount of charge dq at a constant potential V, then the work done is dW, that equals to V dq. This is the equation number 3. In simpler terms, when a voltage exists between 2 points, it means there's a potential difference that can do work. Moving a small amount of charge through that voltage requires a certain amount of work. The equation dW equals to VdQ tells us how much work is needed to move a specific amount of charge dq through a given voltage V. From 2 and 3 equations, where V value substitute in the equation number 3, we get dW equals to Q by C into dQ. This is the equation number 4. Now, the total work done in delivering a charge of an amount Q to the capacitor. It means to find total work done in delivering a charge from Q equals to 0 to Q equals to Q. Limits and apply integration, where integral dW means W. So we get W equals to integral 0 to Q by C dQ. Factor out 1 by C. We get W equals to 1 by C integral 0 to Q into dQ. We know the integration formula, integral x dx, that equals to x square by 2, where integral q dq means q square by 2, and apply the limits 0 to q means q square by 2. So we get W equals to 1 by C Q square by 2. This equation we write W equals to 1 by 2 Q square by C. This is the equation number 5. Therefore, the energy stored in a capacitor is given by U equals to 1 by 2 Q square by C. This is the equation number 6, where W, that equals to U, represents the work done W in a charging capacitor, which is stored as the electrical potential energy U in the capacitor. This energy is stored in the electric field between the capacitor plates. From 1 and 6, simply Q equals to CV value substitute in the equation number 6. We get U equals to 1 by 2 CV whole square by C. Expand CV whole square that equals to C square V square. So now the equation becomes U equals to 1 by 2 C square V square by C. Simplify the fraction. It means numerator C square and denominator C cancelled and remaining term numerator C. So final expression U equals to 1 by 2 CV square. The energy stored in a capacitor is given by the equation U equals to 1 by 2 CV square. Electric potential energy U. This energy is stored in the electric field created by the charged capacitor plates. It's also known as electrostatic energy. The image illustrates the basic structure of a capacitor, which is an electrical component used to store energy in an electric field. Capacitors consist of two insulating material called a dielectric, where conductive parallel plates. These are the two metal plates that store the electrical charge. Dielectric. This is the insulating material placed between the plates, which enhances the capacitor's ability to store charge. Voltage source. The battery symbol represents the voltage source that charges the capacitor. Capacitors work by storing electrical energy when a voltage is applied. When a voltage source is connected, one plate accumulates positive charge while the other accumulates negative charge. This creates an electric field between the plates storing energy. Capacitors can release this stored energy when needed, making them useful in various electronic circuits for filtering, smoothing, and timing purposes. This is our brief explanation of derive the equation energy stored in a capacitor. Thank you very much. Padmam Himam.